December 9th, 2020. A 16-story stainless steel tower, taller than the Statue of Liberty, climbs through the Texas sky, reaching 12.5 kilometers before executing a maneuver no rocket had ever attempted. Starship serial number 8 pivots horizontally, transforming from a vertical missile into a horizontal skydiver. For 6 minutes, this 50-meter steel cylinder falls in controlled descent, its 4 aerodynamic flaps, 2 upper and 2 lower, dancing like mechanical wings to guide it through air thick enough to breathe. Inside SpaceX's mission control at Starbase, engineers watch cascading telemetry streams. Every sensor confirms what seems impossible. The belly flop is working. A rocket is flying like a falling leaf, exactly as designed. Then, in the final seconds, SN8 flips vertically for landing. 2 Raptor engines ignite with blue-green fury, but one sputters out almost immediately. The methane header tank pressure has dropped catastrophically. The rocket slams into the concrete pad at 50 meters per second, the speed of a Formula One car at full throttle, and erupts in a fireball that lights up the evening sky like a second sunset. The headlines write themselves within minutes. SpaceX rocket explodes in massive fireball. Starship test ends in disaster. Musk's Mars dreams go up in flames. Cable news loops the explosion on repeat. Twitter erupts with mockery and schadenfreude. To the world watching, this is failure, pure and catastrophic. But inside SpaceX headquarters in Hawthorne, California, something remarkable is happening. Engineers are celebrating. They're reviewing the telemetry data, pointing at screens, nodding with satisfaction, some even cracking open beers. And then Elon Musk tweets what sounds like corporate spin covering up disaster. Fuel header tank pressure was low during landing burn, causing touchdown velocity to be high. We got all the data we needed. Congrats, SpaceX team. Hell yeah. To the outside world, this looked like delusion. But buried in that explosion was the exact data point they needed. Autogenous pressurization failure in the header tank during flip maneuver. Within 62 days, they'd fix it and fly again. This is the story of how SpaceX weaponized failure itself, turning public disasters into a secret weapon that's revolutionizing spaceflight faster than anyone thought possible. To understand why SpaceX engineers celebrated a fireball, you need to understand the fundamental war being waged between 2 philosophies of building rockets, a conflict as deep as any religious schism. Traditional rocket development is like building a single, exquisite Swiss watch over a decade. Every gear is machined to perfection. Every spring is tested to exhaustion. Every component is analyzed, simulated, reviewed by committees, analyzed again, and tested in isolation before being allowed anywhere near the final assembly. You spend years eliminating every conceivable risk through endless analysis. When you finally wind that watch, it had better tick perfectly, because you've invested so much time and money that failure is literally unthinkable. Career-ending, program-killing catastrophe. SpaceX is like building 100 rough watches, smashing 90 of them with a hammer, studying every broken gear and bent spring, and using those lessons to rapidly create a working timepiece. Then smashing that one too, just to see where it breaks. This isn't recklessness. It's a calculated bet that the cost of hardware is now cheap enough and the value of real-world data rich enough that you can learn faster by building and breaking than by analyzing and avoiding. Consider the numbers. NASA's Apollo program, the gold standard of aerospace achievement, took roughly 8 years from program start to Neil Armstrong's boot print in lunar dust. It commanded virtually unlimited government funding, the full weight of Cold War political will, and a workforce of 400,000 people. That caution was understandable. Apollo carried the prestige of a nation and the lives of astronauts. But it was also glacially slow by modern standards. SpaceX is attempting to build a fully reusable, Mars-capable rocket in a fraction of that time, with private capital, fueled by a culture that allows for rapid iteration based on frequent testing, even destructive ones. Each early Starship prototype cost somewhere between $10 and $50 million to build, a rounding error compared to traditional rocket development. But the data each test generates? SpaceX engineers operate under a radical principle that sounds insane to their competitors. Each explosion costs millions, but the data we gather is worth billions in learning and iteration. This is Elon Musk's personal crusade, and the stakes couldn't be higher. He's betting his fortune and reputation on a philosophy that the entire aerospace establishment considers somewhere between reckless and insane. His personal obsession, proving that humanity can become multiplanetary, but only if we break the slow, risk-averse culture that has paralyzed space exploration for decades. In traditional aerospace, any failure is career-ending. Engineers spend years in analysis paralysis, terrified of being the person who caused the failure. Entire programs get canceled over single anomalies. Careers end. Reputations die. The culture breeds a pathological fear of testing anything until you're absolutely certain it will succeed. SpaceX inverts this completely. Failure is expected. Data is sacred. Rapid iteration is the only metric that matters. When Mark Juncosa, SpaceX's VP of Vehicle Engineering, reviews a test, he's not asking, did it succeed? He's asking, what did we learn? Kate Tice, hosting the live streams, has learned to translate explosions into achievements for confused viewers. We got incredible data on the belly flop maneuver. But the fundamental question remains, hanging in the air like smoke from a rocket explosion. Is SpaceX brilliantly brave or dangerously reckless? Can you really fail your way to Mars? Or is this just Silicon Valley hubris meeting the unforgiving laws of physics? The answer lies in what happens in the 72 hours after a fireball consumes their rocket. Picture this. It's 2 a.m. 3 hours after SN8 has scattered itself across the landing pad in a spectacular fireball. Inside SpaceX's Starbase facility in Boca Chica, Texas, the lights are blazing. Engineers who should be sleeping are instead hunched over workstations, their faces illuminated by screens displaying telemetry data from those final 6 minutes of flight. This is where the magic happens, where catastrophic destruction transforms into actionable engineering breakthroughs within days, not years. Let's dissect SN8's failure like the engineers did. The belly flop maneuver, a never-before-attempted method of aerodynamic control, worked perfectly. Imagine trying to control a 16-story building as it falls sideways through the atmosphere at hundreds of miles per hour, using nothing but 4 metal flaps. It shouldn't work. Physics says a rocket should be aerodynamically stable in one direction, pointy end forward. But SN8 proved you could turn a rocket into a controlled falling leaf, using those flaps to steer with precision. The flip maneuver worked. At the last possible second, SN8 rotated from horizontal to vertical, a gymnastic feat that would make Olympic athletes weep. The vehicle held together through forces that should have torn it apart. But then, autogenous pressurization failure. This is where it gets beautiful in its specificity. Traditional rockets use heavy helium systems to pressurize their fuel tanks, inert gas stored in high-pressure bottles that add thousands of pounds of dead weight. SpaceX wanted something more elegant. Use the rocket's own vaporized methane to pressurize the fuel tanks. It's like a snake eating its own tail, a self-sustaining system that eliminates parasitic mass. Except during SN8's landing burn, the header tank pressure dropped catastrophically. The Raptor engines, starving for fuel at the exact moment they needed maximum thrust, sputtered like a car running out of gas on the highway. Impact at 50 meters per second. Fireball. Data. Here's what traditional aerospace would have done. Spent 2 years analyzing the failure, forming committees, running simulations, writing reports, holding review boards, and maybe, implementing a fix in the next prototype 3 years later. Here's what SpaceX did. High-speed cameras captured every millisecond of the descent. Pressure sensors recorded the exact rate of tank pressure decay. Temperature gauges tracked thermal gradients. Accelerometers measured structural loads. Within hours of impact, engineers knew the precise moment of engine failure, the exact pressure drop rate, and the specific design flaw in the pressurization system. Within days, Mark Juncosa's vehicle engineering team had redesigned the header tank pressurization system. The fix went into SN9 immediately, not in a year, not in 6 months, immediately. February 2nd, 2021. SN9 climbs to 10 kilometers with the modified header tank design. The pressure problem is solved. But now a different demon emerges, because when you fix one problem in a complex system, you often expose the next one hiding behind it. This time, one Raptor engine fails to relight during the landing flip maneuver. The rocket impacts at 50 meters per second, another fireball, another dataset. The propulsion team, descendants of Tom Muller's legendary engine development group, tears into the telemetry. They trace the failure to software glitches in the engine relight logic, timing errors in the millisecond-precise dance of valves and igniters that must bring a dormant engine roaring back to life at low altitude. It's like trying to restart your car engine while falling off a cliff, except the timing has to be perfect to the thousandth of a second. March 3rd, 2021. SN10 incorporates fixes for both problems, the header tank pressurization and the engine relight sequence. This time, all 3 Raptors relight perfectly, their blue-green exhaust plumes blooming against the darkening sky. The rocket executes the belly flop, the flip, the burn. It touches down, upright, intact, the first soft landing of a Starship prototype. Engineers erupt in celebration. They've done it. They've landed a 16-story rocket ship after a controlled belly flop descent. 8 minutes later, SN10 explodes on the pad. Post-flight analysis reveals a methane leak and fire near the landing legs, caused by engines running fuel-rich during an off-nominal landing that compressed the legs harder than designed. The team had solved 2 problems, but discovered a third hiding in the wreckage. This is rapid iteration made visible. You could literally see the evolution from prototype to prototype. SN15, which flew in May 2021, carried improvements from 4 previous failures: upgraded avionics to handle sensor redundancy, reinforced landing legs designed for harder impacts, refined engine relight sequences with better timing margins, and improved methane handling systems with additional leak detection. It landed successfully and stayed landed, standing proud on the pad as the sun set over the Gulf of Mexico. But these weren't just landing problems. The Raptor engine itself represents one of the most significant advances in rocket propulsion in decades. A full-flow staged combustion cycle running on methane and liquid oxygen, achieving chamber pressures beyond anything in operational service. Every test fire, every explosion, every anomaly refined the engine. Raptor 1 evolved into Raptor 2, then Raptor 3, each generation incorporating failure data into fundamental redesigns of turbopumps, injectors, and combustion chambers. The revelation that emerges from this pattern: SpaceX isn't just accepting failure. They're engineering tests specifically designed to fail in useful ways. They're deliberately pushing systems past their limits to find the exact breaking point, because that's where the most valuable data lives. It's the difference between asking, "Will this work?" and asking, "How exactly will this break, and what will that teach us?" But this philosophy of embracing failure only works if you're solving the right problem. And for Mars, that problem is one that has bankrupted every company that's tried to solve it. Every explosion at Starbase is ultimately about solving one problem: the tyranny of the rocket equation. Here's the brutal economics of traditional spaceflight. Imagine building a Boeing 747 for $400 million, flying it once from New York to London, then crashing it into the Atlantic Ocean. Now imagine doing that for every single flight. That's how we've been getting to space for 70 years. A traditional expendable rocket costs anywhere from $60 million to $400 million per launch. You use it once, and most of it burns up in the atmosphere or sinks to the bottom of the ocean. It's like buying a new car every time you need to drive to the grocery store. This economic insanity is why space remains the domain of governments and billionaires, rather than ordinary people. SpaceX's goal sounds simple, but borders on the impossible: full reusability that reduces cost per launch to under $2 million, just the cost of fuel and operations. This is the only way Mars colonization becomes economically feasible. This is the only way humanity becomes multiplanetary. But full reusability requires simultaneous breakthroughs in 4 separate engineering domains, each of which has defeated every previous attempt. First, landing technology for a vehicle traveling 17,000 miles per hour during orbital re-entry. You're trying to land something moving 22 times faster than a speeding bullet, something that's been heated to 1,500 degrees Celsius by atmospheric friction, something that weighs as much as a loaded 747. Second, thermal protection systems that survive re-entry temperatures hot enough to melt steel, then can be rapidly inspected and cleared for the next flight without months of refurbishment. Third, rapid turnaround requiring minimal refurbishment, ideally landing, refueling, and launching again within hours, like an airplane. Fourth, engines that can fire dozens of times without replacement, surviving the thermal and mechanical stresses of repeated startups, shutdowns, and throttling. Each of these is a decade-long engineering challenge that has consumed billions of dollars in previous attempts. SpaceX is solving all 4 simultaneously through their methodology of rapid iteration and calculated failure. The full Starship stack, Super Heavy booster, and Starship upper stage combined, stands 120 meters tall. That's taller than Big Ben. It produces 75 meganewtons of thrust at liftoff, using 33 Raptor engines firing in perfect synchronization. To put that in perspective, that's more than double the thrust of the Saturn V that took humans to the moon. The upper stage alone is 50 meters tall, carries 1,200 metric tons of propellant, enough to fill nearly 500 tanker trucks, and must be capable of landing on unprepared Martian surfaces with no ground support infrastructure. The full system has a gross liftoff mass exceeding 5,000 metric tons, the weight of a naval destroyer. You don't learn to land something like that by running computer simulations. Computer models are useful, but they're always approximations of reality. They can't perfectly capture the turbulence of supersonic airflow over those 4 flaps, the sloshing dynamics of cryogenic propellant during a flip maneuver, or the way landing legs compress when a 50-meter tower touches down on uneven terrain. You learn by doing it, breaking it, and doing it again. SN8 proved aerodynamic control during the belly flop descent. That data validated years of computational fluid dynamics work and revealed edge cases no simulation had predicted. SN9 proved the flip maneuver could survive multiple attempts and identified the engine relight timing problem. SN10 achieved the first successful landing before exploding, teaching them about landing leg loads and fuel-rich engine shutdown. SN15 landed and survived, incorporating lessons from every previous failure. Each explosion eliminated one failure mode, bringing the entire system closer to operational reusability. It's like solving a massive jigsaw puzzle, except each piece costs $20 million and explodes when you try to fit it in the wrong place. Traditional aerospace companies, Boeing, Lockheed Martin, Arianespace, spent decades and billions on reusability concepts. The space shuttle was supposed to be rapidly reusable. Instead, it required months of refurbishment between flights and cost more per launch than expendable rockets. Lockheed Martin's VentureStar program, intended to replace the shuttle, consumed $1 billion before being canceled when the composite fuel tanks kept failing. Arianespace studied reusability and concluded it was economically impractical. All of them abandoned full reusability as too difficult or impossible with current technology. SpaceX's willingness to embrace spectacular public failures is the only thing that's made progress possible. While competitors were still arguing about the theoretical feasibility of propulsive landing, SpaceX was learning from their 3rd landing attempt explosion. The moment of realization hits like a physical force. SpaceX isn't competing with other rocket companies. They're competing with the fundamental economics of spaceflight itself. Every explosion is an investment in breaking the cost curve that has kept humanity confined to Earth for all of history. And that brings us to today. where SpaceX's strategy of weaponized failure has brought them to the edge of something no one thought possible. Let's zoom out and see what's actually been accomplished here. We started with what looked like reckless explosions and corporate spin, a billionaire's ego project creating spectacular fireballs for YouTube compilations. But we've discovered the truth beneath the smoke. SpaceX has fundamentally redefined what success means in aerospace. They've proven that in the race to make humanity multiplanetary, the fastest path isn't the safest one. It's the one that learns the most from each failure. Traditional aerospace spent decades avoiding failure and made incremental progress measured in single-digit percentage improvements. SpaceX embraced failure as a tool and achieved in 5 years what was supposed to take 50. When SN8 hit the ground at 50 meters per second because of low methane header tank pressure, this would have traditionally been viewed as an unacceptable disaster, the kind that ends programs and careers. SpaceX saw a successful test of aerodynamic control, flap authority, and engine relight sequences that happened to end with vehicle loss. The distinction isn't semantic, it's philosophical. The data from that failed landing was immediately fed into SN9, SN10, and ultimately SN15, which nailed the landing 4 months later. 4 months from catastrophic failure to successful landing. Traditional aerospace would still be forming the committee to investigate the failure. Think about what's visible in the wreckage of those early prototypes. SN8 proved you could control a falling skyscraper with metal flaps. SN9 proved you could flip it vertical at the last second. SN10 proved you could land it, at least briefly. SN15 proved you could land it and keep it landed. Each explosion was a program success because it answered questions that couldn't be answered any other way. The explosions weren't setbacks. They were the price of admission to a future where Earth isn't humanity's only home. Consider the alternative timeline. If SpaceX had followed traditional aerospace methodology, they'd still be in the design review phase, running simulations, forming committees, writing reports about the theoretical feasibility of propulsive landing. No hardware would exist, no data would have been gathered, no progress would have been made. Instead, they've already landed a Starship prototype. They've already proven the belly flop maneuver works. They've already demonstrated engine relight at altitude. They've already gathered more real-world data on rocket reusability than the entire aerospace industry collected in the previous 50 years. And they did it by being willing to blow up rockets in front of the world. The next time you see a Starship prototype explode in a spectacular fireball, remember, you're not watching a failure. You're watching the future being built one calculated disaster at a time. Every fireball at Starbase isn't a rocket dying. It's a data point being born. And somewhere in the accumulated wreckage of a dozen destroyed prototypes lies the exact knowledge needed to build the vehicle that will carry the first humans to Mars. That's not failure. That's the sound of the future arriving ahead of schedule. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.